Hey everyone, sorry I can't be there today. Don't worry about me, I'm absolutely fine. I'll explain all when I'm back. But today, as I said we would do last lesson, we'll just go through this example here. Now, this is a slight twist on all of the stuff that we've been doing so far. We've been looking at slopes where we have gravity down, a reaction force that is not necessarily vertically up, but is perpendicular to a surface that we're on, and then all forces that could act in any way. The hardest thing that you have to do is to figure out which way friction goes, and then from there you can resolve all your forces. Now, this is a slight twist on the question because unlike previous ones where we're either on a horizontal surface or on a plane, resting on a plane, this is a ring. And the thing is, what they can do with a ring is they can go from horizontal or up from horizontal to completely vertical. And what you'll notice this changes is the reaction force. No longer are we resting on something and then a reaction force up from that surface. Instead, we're kind of like being held in place by the reaction force, this time horizontally. So that reaction force has to act this way. You might be thinking, well, what happens here? And actually, it's a good example to kind of really investigate your understanding of how these forces work, because your intrinsic understanding from real life would be that, well, this is being held in place by the pulling effect, right? It's clearly being held in place by this string, right? If you didn't have this string, it'd just be falling down. So there is a pulling effect. And you first might think, well, it's this force that keeps it up. But you know from your understanding of mechanics now, or you should at least, that we only consider forces in directions. So we know that this way we are in equilibrium, and that one is relatively easy to kind of square away in your head, right? But this way we have to be in equilibrium as well. And this force, the force that acts on this ring here, there is a weight. That weight is 0.2 g. So there must also be a force going up. And the pulling force to the side here does not explain what is keeping it up, actually. I think in this scenario, it's kind of hard to think of friction, because when you're thinking of a pole, yes, this is a rough vertical rod. It is rough. You've been told that. But when you're thinking of a rod, you're tending to think about something not necessarily that has like friction, that is rough, that would keep something up. But in all cases where something is being suspended on a rod like this, there must be some sort of friction, because it is not not purely the tension from the rod that's keeping it up, and it's not any of these sideways forces here. There is a component of tension that's keeping it up, but there is also potentially a component of friction that's keeping it up as well. Friction will act vertically as well. And that friction doesn't come from this force, but rather, again, this force. It comes from the reaction that is acting horizontally. And there is a reaction force horizontally. There is a reaction that's going to be going this way, because there is a horizontal force this way. And actually going back to our horizontal equilibrium, if the force acts this way, then there has to be an equal and opposite reaction that way as well. So we'll get into that now. First, to read the question. 0.2 kg, which means that we have a downwards force of 0.2 g attached to the end of a light inextensible string, same as always. The ring is threaded onto a fixed rough vertical rod, so it's rough, which means that there will be friction. Given that the ring is in equilibrium and the tension is 10 newtons, the string is taut and tan theta equals 12/5. Find the magnitude of F, which is the friction, and to state the direction of F as well. This actually, by the way, is the last question from the second set of exam questions I posted on statics. So if you want to have a look at it there, it's worded slightly differently, but obviously I've had to write it out, so I've just written as it is there. Right, find the magnitude of F. Now, this is what we were talking about before, in that there must be some friction acting. We actually don't know yet if it's either up or down, because we've not been told that it's in limiting equilibrium, just that it's in equilibrium. We know what the angle is, and we know what the tension is here. So let's draw a force diagram. We have our ring here. We said that we must have that force of 0.2 g. We must have other forces as well. We must have the tension here, which is 10 newtons. We know that that angle there is theta, which is given by this, but we'll get back to that. And then we have a friction. Now, I was talking about friction holding it up before, but actually in this case, when it's not limiting equilibrium, we don't know whether friction is holding it, is pulling it up, or actually causing it not to slip up the plane and therefore pulling it back down. This tension might actually be so great that this is supposed to slip up the plane, but the friction is holding it back. How do we work out which direction it's going in? Well, the answer is kind of that it doesn't matter, right? I can choose, for convenience's sake, friction goes up. Now, it might not go up. If it doesn't go up, what do you think will happen? I'm pausing for you to have a think. If friction doesn't go up, if actually friction acts downwards, what do you think will happen when we solve? Well, what you should be saying is that we'll solve all the same, and the answer that we'll get will actually be a negative answer. And that's fine. We just have to interpret that correctly. So whatever friction is, we say it will be downwards, okay? Well, let's do all of this. We need to resolve. Before we resolve, let's get this triangle out of the way. If we have a triangle where tan theta equals 12 over 5, that means opposite over adjacent is 12 over 5. And that gives us a a trigonometric triangle, 5, 12, and the missing one would be 13. Worth just writing out what sine theta and cos theta are then. Sine theta will be opposite over hypotenuse, so 12 over 13. And cos theta will be adjacent over hypotenuse, which is 5 over 13. Okay. So now let's resolve. Now, this is kind of this is a slightly weird question because it gives you a situation which is not in limiting equilibrium first, so it doesn't require F max. That's an important thing to note here. Notice how it's saying find the magnitude of F, not F max. It's just the frictional force that is keeping things in place here. That doesn't necessarily mean it's not that it's the maximum value of friction, which means that you shouldn't be thinking about R. You don't need to think about R here because we don't know, and ignore that because that's part of the second part of the question. We don't know what the coefficient of friction is, so even if we knew what R was and we calculated it, it wouldn't help us. We wouldn't be able to find what F max was, and we wouldn't want to use F max anyway. Instead, we actually only need to look horizontally here. We can see that there are forces being applied horizontally. One of them is the component of this 10 newtons. We have 0.2 g downwards, and then we have F. So let's resolve this then. We have forces going down. What are those forces going down? That will be 0.2 g. We have forces going up. That will be F. And then we have a vertical component of 10 newtons, which will be up through the angle cos theta. So what I can write here is 0.2 g minus 10 cos theta equals F. This is the classic case of where it's slightly confusing because cos theta looks like it's an unknown, but we know what the value is. So we have here 0.2 g minus 5 over 13 times by 10 equals F. Now, if you stick that in your calculator, that will actually give you, where have I got it here? Negative 1.93. So, as we said before, we were guessing at where F went, but now that we've worked it out, we can see that it's negative, and so it's not in this direction we initially put it, it's in fact downwards. So we say that for A, we have 1.93 newtons, and the direction is down. So what's happening here mechanically is that that force, 10 newtons, the force from the string, is actually too big. It's greater than gravity, which means that friction is needed to actually pull it down to stop it from slipping up. What I could have done is, from the start, worked out which is bigger, 10 cos theta or 0.2 g, but when it comes to more complicated questions, you're probably better off just picking a direction and then going with it, and then figuring out what that means after the fact. Okay, for part C, we go away from this example a little bit, and T is now able to vary. So T is no longer 10 newtons, but T could be anything. And what it's asked you to find is the minimum or maximum values of T. Again, it just says it's in equilibrium here, but because now we're not talking about minimum and maximum values, the fact that it's limiting equilibrium is implied. So we have to be using the maximum value of friction in order to get the minimum and maximum values of T. How do we get a minimum and maximum then if we're using Fmax? Well, if this force here, this pulling up tension, was as small as it could possibly be, so this is a really weak force here, then what would happen to the ring mechanically? Or what would be about to happen to the ring? If this force is really small, the ring should be about to fall down. If the ring is about to fall down, what does that mean for friction? Well, it means that friction must be trying to pull it up. So the only forces are 0.2 G down, then a weak tension up, and then this Fmax pulling up as well. In the other way, so if the force here is as big as it can possibly be, then this is about to be yanked up the pole, which means that friction must be acting down the pole. It's trying to oppose the motion. And that's how we get the maximum and minimum value of T, is by inverting the direction here. The important thing, of course, as we discussed, is that we are using the maximum value of friction. So the first thing to do is to find what that max value of friction is. And as we know, Fmax equals mu R. Mu in this case is a quarter, so we just need to work out what R is. We can kind of use the vestiges of this diagram here, but I'll draw one again to show that now we are working with an unknown friction. So we have the same angle there, there's nothing to worry about. We have T, which is an unknown tension, and we have R pointing out that way. Now, it doesn't matter which way friction is going when it comes to this diagram here and when it comes to R. Friction will be vertical, the weight is vertical, so in terms of calculating R, we just need to resolve horizontally. So R equals T sine theta, it's opposite that angle. That's what R equals. Let's immediately get rid of this sine theta and replace it with what we knew sine theta is over here. So R equals 12 over 13t. Fmax is mu R, so Fmax equals 1/4 times 12 over 13t. Fmax equals, what's that, 3 over 13t. Okay, so just from this diagram here, which doesn't even include the vertical forces, I have got a expression for Fmax in terms of T. What I need to do now then is to consider the two different situations. One where Fmax acts upwards, and this will give me my minimum value of T because we're about to slip down the plane, so T is too weak. And then we have one situation where Fmax acts downwards, but we'll get to that in a second. So when Fmax acts upwards, we also have this downwards force, of course, 0.2 G. We're still in equilibrium, so what we have is 0.2 G equals T, this is cos theta, plus Fmax, which is 3 over 13t. So we have 0.2 G equals, cos is 5 over 13, 5 over 13t plus 3 over 13t. So 0.2 G equals 8 over 13t. Sorry if you can't read that, it's getting quite small now, I appreciate. Anyway, you solve that, you divide by 8 over 13, and you get T is equal to, I think, 3.185, which obviously you round up to 3.2 or 3.19. And the other way is pretty much the same. We just have our diagram now, which will have Fmax down. as well as 0.2g. Oh, this is going to be horrible to solve up here. I'll just go on to, I can't go on to new page. I'll go up here. So if Fmax is going down and 0.2g are going down, my equation will look like this. 0.2g plus Fmax is equal to t cos, is it theta? Yeah, theta. That means 0.2g plus 3 over 13t equals cos theta again is 5 over 13t. And so 0.2g equals 2 over 13t. And so t equals 12.74, 12.7. So 13 or 12.7. Okay. I appreciate that got smaller and smaller as it went on, but hopefully you were following the mechanics behind it and the maths behind it. Obviously, let me know if you have any questions there. You just need to finish off all of those statics questions. I've posted 2 sets of them there. If you can do all of those, then you're in a pretty good position.